welcome to this live lesson for Earth Week 2023. We're going to be learning all about how do we know about climate change. Before we connect up to our wonderful team of scientists at the University of Exeter, I'm just going to go over a few bits and pieces on the housekeeping side. Hopefully you can see that to the side of the screen there's a place to put all the live lesson. There's also a thumbs up button beside each of the questions, so if you see one you really like, do click the thumbs up button and we will answer those in order of popularity. If there are any technical issues, don't put them in that chat. There's a little chat icon at the bottom right hand corner of each page of the Encounter EDU website, and if you're having any technical issues, as quickly as possible. But just to welcome, we've got an amazing array of countries who have joined today. We've got students from the UK, Czech Republic, France, Poland, Romania, Greece, Malawi, Spain, the UAE, Jersey, Norway, and Italy. Welcome, one and all, wherever you're watching from. And a few very special shout outs. We've got Mr. Shaw's class from Penthorpe School in Rudgwick. Great to have you with us. We've got Year 9 students who are at Ullswater Community College in Cumbria in the UK. And we've got a wonderful Scottish primary school. I hope you'll be able to follow along. This lesson is aimed at secondary students, but a big welcome to the wonderful P6 and 7 class at Little Mill Primary School who love learning about the environment. Hopefully this will add a little bit of rocket fuel to your knowledge, but really hoping you enjoy the live lesson. And just one last note is there is a student sheet that accompanies this live lesson. We'll be referring to it in the different sections throughout. So hopefully you have that with you. But without further ado, let's meet our wonderful scientists. Good morning, James and Zoe. How are you?
We're fine, thank you.
Great, thanks.
Yeah.
Good to be here.
Brilliant. Wonderful. Thank you so much for being part of this live lesson, part of the Convex Seascape Survey Education Programme. Can I ask?
Pretty much my whole career.
Yeah. And hello, I'm Zoe Roseby. I'm also a marine geologist, and I've been working on reconstructing past environmental change using sediment cores like what we're going to be discussing today.
Perfect. And this is part of the Convex Seascape Survey, and that's a sort of a 5-year mission. Am I right? What's going on there?
Yeah, I'm sort of trying to work out where all the carbon is in the Earth system, and we don't know exactly how much carbon's there, and it's really important for us to know because there are certain activities like trawling that can remobilize that carbon and create an additional problem in terms of greenhouse gases in the atmosphere.
So if I get that right, all the sediment, the sort of muddy, sandy bottom of the ocean, it's a habitat just as important as the terrestrial, the land habitats we may know better. And so we need to think about looking after it just as carefully.
Yeah, exactly. And that organic matter kind of comes from sort of small microscopic organisms living in the water column or kind of muds and sediments that get washed out from land through our rivers and into the ocean. So all these very, very tiny particles are settling onto the seafloor over the time, and they contain carbon, and they might provide a vital store, and that's what we're trying to find out.
Brilliant, thank you. Well, let's dive into our learning. We've got this first section, what affects climate change, and for students that's the first activity on your student sheet, and we can probably sort of see a graph coming up on screen, this classic sort of graph which is sort of looks like a sort of goes up and down. This is about 800,000 years of climate history. What's going on? I mean, why isn't there sort of a steady line?
Right. Okay. For maybe a few decades now, we've discussed history, as it were, that we've got these regular changes in the Earth's climate, and they go from what we call ice ages, when we have, over the British Isles, we had a huge ice sheet, to relatively warm phases like the one we're now in. And we know that those are being paced, they're being driven or forced by changes in the orbit of the Earth around the sun. So sometimes the Earth system is closer to the sun and we receive more sunshine, more radiation from the sun, and that gives us the warmer phases. And then other times we're further away, and that gives us the ice ages when the great ice sheets build.
And it's not just the sort of Earth orbit, and I think students, you can sort of put an N or an H depending on whether these are sort of natural factors or ones that could be sort of influenced by human activity. But there are a few other factors that affect Earth's climate.
Yes, exactly. So James has already mentioned the Earth's orbit, which changes over time, and it changes in a cyclical way. So we go through common phases of warming and cooling, a bit like we go through changes in seasons over the year. So that one is kind of predictable. Now we've understood how it changed in the past. We also have changes in the sun strength. So, on a hot day, you can feel the warmth of the sun, and that changes over time as well. Also, in a way which changes on a kind of in a cyclical nature as well. We also can have more instantaneous impacts related to kind of meteorite impacts or volcanic eruptions. In the case of volcanoes, they produce huge ash plumes which go up into the atmosphere, which can have an impact on the amount of warmth that we're receiving on Earth. And then we've got things like land use changes. So a lot of you may have seen kind of in documentaries or through discussions with your friends and family, or even your observations of how you kind of go out on walks, that you see some areas where trees are being planted and some areas where trees are being removed. And trees provide they're a really vital habitat for absorbing carbon from the atmosphere and changing our climate. So land use change has an impact, and as does our release of greenhouse gases. So this will be something that I'm sure lots of you will be familiar with. So human activities can release these greenhouse gases. The more of them we release into the atmosphere, the more heat is trapped in Earth and causes global warming as well.
And just this is amazing, best summary I think I've ever heard. Thank you very much, both of you. But just to sort of, greenhouse gases levels have changed over time through natural as well as human activity.
Absolutely, we've got fantastic records from the ice sheets where we can drill down into the ice sheets and produce these ice cores. And trapped within the ice cores, you've got little tiny bubbles, which are little samples of the atmosphere at the time in the past, and we can date the ice cores. So we can go back to, 120,000 years ago, and we can extract very carefully the gas from within the bubbles and measure the amount of greenhouse gases, CO2, methane, and other greenhouse gases within those bubbles. From that, we can tell that way before the Industrial Revolution and way before the transition to agriculture, in fact, there were natural fluctuations of CO2. So greenhouse gases are an entirely natural forcing for climate change within the Earth system. And in fact, if we didn't have greenhouse gases, the equilibrium temperature of the Earth system would be about minus 18 degrees centigrade. So greenhouse gases are a jolly good thing, and we wouldn't be here without them. But sometimes we can have too much of a good thing.
Well, I think we'll coming on to sort of what the future may look like towards the end of the lesson. So brilliant, thank you very much. I hope you've got that section done on your student sheet. We've talked a little bit about sort of ice cores and everything else, and how do we know what's that sort of evidence that we have for the sort of change in Earth's climate over time? Because I mean, we didn't have sort of dinosaurs and lab coats. We didn't have these thermometers going back over time. And you've mentioned ice cores. Are there other ways that we can reconstruct the past climate?
Yes, exactly. So as you say, we've discussed ice cores. So on ice sheets, we kind of get snow accumulating over time and trapping some of the properties of the atmosphere at the time that snow was deposited. We get a similar thing with sediments as well. So we spoke before about how the Convex project is looking at these fine particles of sediment that fall onto the sea floor. And we'll come back to this, but these layers of sediment also trap properties of the surrounding ocean and climate. We've also got things like tree rings, and James has got an example here. So tree rings accumulate, or they grow outwards over time as the tree grows. And as those rings grow, they'll also track properties about the climate change. So that's a great archive as well. We see a similar mechanism happening in corals. So corals also grow over time and they accumulate these growth bands, and we can look at the changes in the properties of those to relate those to changes in the properties of the ocean over time. And then we've got a couple of more recent things. We can look at historic documents. Humans have an amazing, we're really interested in the environment, and we've been monitoring and tracking environmental changes long before we were really interested in climate change or even doing science kind of as a profession. People are interested in the extent of glaciers in their local environments or historic sea level change. So we can go back and look at those historic documents. And then more recently, we've had scientific instruments, for example, satellites that can measure sea level and sea level changes. So, those are more recent inventions.
And what I'm particularly keen on are these things. You can see this shell. That's a bivalve. That's the Icelandic clam. And you might be able to see on the outside of that, you might be able to see those ridges. And they are growth increments. They are annual increments, just like a tree ring. And this particular species is the longest lived animal known to science. And these can live over 500 years. And we can examine each individual increment and work out exactly which year it is, and reconstruct the climate from that year, from these books of the ocean.
Brilliant. And there's this term that I've come across a lot, the difference between something called a proxy and a direct measurement. And I think that, we're asking our students to think about the difference between what clues you've mentioned that are sort of proxies and which ones are sort of direct measurement. And what is a proxy? To start off with.
So a proxy is, as you say, dinosaurs weren't running around with white coats on measuring the climate of the Jurassic. And we only have these scientific instruments that Zoe mentioned. We only have records of those going back on land, even just a few hundred years. And in the ocean, we've only got just a few years, just a few decades at most. So we need to use other tools to find out about the climate in the past. And the way we do this is through these, what we call these indirect measurements via proxies. So for instance, you could find a particular species of shell, it might be a mollusk or something else. And at the present time, we might know that it lives in a particular seawater temperature, or it might be a plant and it grows in a particular temperature up a mountain, say. And by finding the fossil remains of those species in sediments, we can date the sediments and we can say, well, we've got this very cold species in this part of the record. That's a proxy for the temperature of the time. So it's an indirect measure of a variable that we can calibrate or measure at the present time.
And so that, tree rings are like that, because we can see the sort of like the difference between the light and the dark would be a clue of what the temperature was at the time, and corals and so forth.
That's right. The reason we have tree rings is because of the change in the seasons. Tropics, where you have less seasonal variability. In fact, you have trees that don't have particularly good tree rings. So that's a demonstration that the climate is essentially forcing the pattern of rings.
Brilliant. One of the pieces I know we're going to get to, we had a great day with you, James, last week, and we're looking at marine sediment cores. I think one of the ways that we can sort of think about reconstructing past climate. Just to sort of finish off this section is really and is a brilliant explanation, looking at all the different ways, either proxy or direct measurement, that we can reconstruct climate. So we're now going to move on to this examination. We spent a good hour in your lab. I feel like I've always like a sort of degree in marine sediment analysis. I know it takes much longer, don't worry. But it was wonderful. And I think just to give students watching an idea, what is a marine sediment core, and how do you go about getting it?
Yeah, so marine sediment cores. So I spoke before about the kind of the settling of these fine particles through the ocean and that they accumulate on the seabed. So the seabed then becomes layered, and the sediments at the bottom are the oldest, the sediments at the top on the seabed are the youngest. And within the kind of the layers of those sediments, there are kind of proxies or clues of the past environments that we want to be able to kind of extract. So we need to find a way of taking all of these layers from the sea floor to reconstruct environmental change, and we do that using a sediment core. It looks a bit like a really big straw that we plunge into the sea floor, and then we pull out this tube of sediment. And as I say, the sediments at the bottom are the oldest and the sediments at the top are the youngest. And they have different layers through them. And we look at those different layers to reconstruct how the ocean properties have changed over time.
Brilliant. And then I think you bring them back to the lab, and then you're laying them out, and you're doing this analysis. So we've got two cores. I think we looked at, James. We've got the first one. Was it the Goeben spur?
Yeah, it's a site in the North Atlantic where I recovered this core in 2004 from just over 3,600 meters water depth, so that the sea was between 3 and 4 kilometers deep. And on the seabed in that particular location, which is, as you can see on the map, it's just southwest of Ireland. We've had relatively slow sedimentation, but over a long period of time. And so the core in that case was about 10 meters long, and it covers about the last 130,000 years of ocean history.
Wow. Well, we've got some video of you giving me a tour of this core. It's 10 meters and 130,000 years. Can you give us a sort of brief potted history? I think we started at the present day.
Okay, if we go backwards, then if we start at the top of the core, we've got a relatively short section which is quite light in color. It's quite chalky, in fact. And the reason it's light in color and chalky is it's rich. It is literally chalky. It's rich in calcium carbonate. And that's made up of all the it's all lots and lots and millions of fossils, in fact, which are made of calcium carbonate. And they've accumulated over time. And then if we go further back down the core, we find that it goes much darker, much less chalky, into a kind of dark grey-brown colour, which makes up the majority of the sediment core. And then towards the bottom, it goes chalky again. In a sort of oscillating way. There are sort of 3 bits of chalky with darker bits in between. So the colour of the sediments are changing, and we can link those changes of colour to the changing climate.
Brilliant. So you spoke about the dark patches occurring from something like this picture behind me. This iceberg with a bit of rock stuck in it. If I know it's not very technical terming.
Yeah, exactly. So that the icebergs will carry sediments that they've eroded from land. They drift out into the ocean, and over time they melt, and all that sediment that's trapped kind of gets melted out and drops on the sea floor over time, and that's what brings a lot of these particles that are darker in colour.
We've both been in Antarctica, haven't we, on research vessels at different times, and in Antarctica you've got the edge of the ice sheets breaking off. And quite a lot of the icebergs you can see have got darker lines within them, and that's the sediment that they're carrying. And as they travel across the ocean, they just melt, and the sediment drops out. And of course, it sinks very slowly, and larger particles a bit faster to the seabed. And so it's those particles that make the sediment a bit darker in color. So the darker sections represent the cold sections when we've got lots and lots of icebergs, and the lighter bits, which are composed of the chalky fossils, represent the warmer episodes.
So essentially, if you did a color mapping of the core, you could start to get an idea of how the temperature was changing.
Yeah, you can get a very quick. It's actually really exciting when you you slice one of these cores open for the first time on the ship, and you open it up, and you just see these fantastic changes. I remember being on a ship off Africa and just seeing all these red and yellow changes, and they represented dust being blown in from the Sahara over millions of years. It's really exciting, that moment, because it's so visual, and you can see the changes straight away.
Now, both of you've given me a tough term to say, but I'm going to go for it, which is another clue that we talked about. Is it foraminifera?
Yes, yeah, that's it, foraminifera.
Foraminifera, there we go. I'm going to get it second time. First of all, what are they? I think we've got a slide just generally, about, just to show a sort of mix of them. What is a foraminifera?
So foraminifera are unicellular organisms, so they're incredibly tiny. We use microscopes to look at them. They're smaller than a grain of sand in general. And we've actually got some on the screen just behind James there. So foraminifera live in the ocean. They can live in the water, or also some species live in the sediment itself. So we call those planktonic, that live in the ocean, or benthic, they live in the sediments. And they kind of produce these shells. And the shells we call tests, and they are made of calcium carbonate. So that's, in general. So this is what James is saying, that the calcium carbonate has a white color. So actually, when the sediments are paler in color, it's because we've had a lot of these foraminifera and another species called calithrophores that are very white, and they deposit on the sea floor. There's more of them when it's warmer. So that's why we have whiter colors and warmer temperatures, because there's more foraminifera. But they're also really, they're a really useful clue, because different species favor different environments, as we see across a lot of different kind of plants and animals. So some species prefer cold water environments, and some species prefer warm water environments. So when we're looking at our sediment core, if we see intervals where we have more of the warm species, we know that the ocean was warmer at that time. If we see intervals where there are more of the cold species, we know that the environment was cooler at that time. So we're really using the kind of proportion of cool and warm species to reconstruct temperature going back in time. So yeah, they're a really, really quick, key proxy for people that study past environmental change.
And I think we've got sort of picture, we've got sort of, is it, I can only say MPS before I get...
Yeah. It's got a very long name, but it's one of our most useful. Forams, we say for short. So we don't say foraminifera every time. We say forams. And it's called Neoglobocardrina pachyderma sinistral. And it's a foram which, it's a planktonic. It's one that lives in the surface ocean. But it's the only species that lives in the very cold Arctic waters north of what we call the polar front. So it's a really, really good indicator of really cold conditions. So if we have a lot of that particular species in the core, and in the darker sections we find almost only that species, and so it confirms the interpretation that those sediments represent the cold sections. We find almost only that species, but in the chalky bits we find a huge assemblage of many different species, some of which in this latitude of the North Atlantic are verging on the subtropical. So they're certainly temperate and a much broader range of species.
And these are smaller than a grain of sand. And you've got 10 meters in 130,000 years. How much work is it to actually look at all the different range of species at any one time, and who gets to do that?
Yes, you're
Zoe gets to do that.
I get to do it. No, it's a real labor of love, I'd say. It takes a long time. So we're looking at kind of 10 meters of cores, and we usually take small slices out of the core at regular intervals. So that might be every 10 centimeters. And then from each one of those samples, we have to process the sample, we sieve the sediments so that we can see the foraminifera, and then we count the proportion of the different species using a microscope. And each one of those samples might take half a day if you've been doing this for, quite a long time. So we're looking at months of work if you want to kind of prepare samples from one core, take your individual samples and count the different foraminifera species. We're looking easily at 3 months of work, if not more, for a reconstruction from one core. But it is really exciting when you kind of initially plot all of that data together and you've got this story about how the environment's changed in the past.
Well, amazing amount of dedication and concentration. Thank you. this we had a second core as well. This one looked sort of, to use non-scientific words, sort of shorter and muddier. If where did that one come from?
That one we only took about this time last year. Actually, we took it from much shallower water in the Orkneys, north of Scotland, in a place called Scapa Flow, and in just a few tens of meters of water. Certainly not the water depth that we of the first core we were talking about, and that's about only 3 meters in length or so. But actually, we have about 10,000 years there. So the sedimentation rate is much faster, and quite often in shallower water we have more sediment per unit time, as it were. So we've got a more detailed record, as it were, in that core.
And when we were looking at it together, I saw sort of what looked like sort of whole seashells that looked like they could have been picked off a beach. Are those part of the fossil record?
Yeah, they are, just like the Arctica that I showed you. This one, in fact on that cruise we took several sediment cores where we had these very long-lived shells actually within the sediment, and they can provide us with really detailed information, because we can actually go down into the individual years. Whereas when we analyze the sediment records and we look at the forams, very often, one sample might be 100 years, or it might, even in a deep sea core, it might be 1,000 years or 2,000 years. But we can get down to the individual year within these larger fossils.
And I think when we were chatting before we started the lesson today, we're talking about not just physical clues, which we've sort of looked at so far, but also sort of chemical clues as well. Can you briefly touch on what some of the sort of chemical clues that we might find?
Yeah, so as these kind of the shells build up of these organisms, whether that's kind of in like the seashell that James just showed, or the foraminifera that we were discussing before, they make their shells using kind of the properties of the seawater. So like they'll grow growth bands, or the foraminifera grow these kind of very tiny shells made of calcium carbonate. So as they build their shells, they're kind of using the surrounding water for the kind of the properties that they use to build them, and they therefore trap the properties of the ocean at the time that they were developing. So, for example, we can look at isotopes. So oxygen isotopes are a really interesting way of looking at the volume of ice that we had on land. So that relates to kind of cool periods versus warm periods. So we can look at the chemistry of the shells themselves to tell us something about past environments.
I mean, it's been absolutely amazing. I mean, just to think that within these sediment cores, we've got these different clues. We've got the color clue, and I'm just, I know that students have this on their sheets to make notes on, which was the different, whether it's sort of icebergy rock or chalky structures and shells. We've got the different species, which of forams. Now I know not to have to say every single syllable, and I'm not even going to try and pronounce the different species names. And then that wonderful bit at the end where we've got the growth bands in shells and moving into that sort of chemical analysis of the isotopes, which give us and those different isotopes relate to different climatic conditions.
Yeah, that's right. Yeah, the different oxygen comes in different isotopic species, different types, and the main ones we deal with are oxygen 18 and oxygen 16, and they have slightly different atomic mass. So we would dissolve the shells, the forams, and release carbon dioxide, dissolve the shells in acid, and using a really sophisticated piece of equipment, we can measure the number of the different isotopes within that sample, and that tells us whether we're dealing with a very cold ocean or whether we're dealing with a very warm ocean.
Brilliant. Thank you so much. And I think just moving forward, obviously, when we talk about climate change at the moment, most of the conversation isn't about the past 130,000, 800,000 years, but it's about the future. And I think we can sort of share these projections that go into the future from different scientific bodies have different ideas about how climate is predicted to change. How does your work and the work of working with sediment cores help us sort of look into the future?
Yeah, I mean, it kind of is useful in a couple of ways. So it's really important for us to be able to understand what's controlling climate change. So as you've seen kind of during this lesson, that the climate has changed through Earth's history long before humans were kind of influencing the environment. So we've kind of gone through periods of warm and cool temperatures that relate to, as we've discussed, changes in solar radiation, the Earth's orbit around the sun, the volcanic and meteorite activity. So that's really important for us to understand, because a lot of these are cyclical in nature. They are predictable, and we can see what temperature on Earth would be like now if we were only experiencing those natural climate kind of mechanisms without the addition of carbon dioxide from human activities or deforestation from human activities that kind of removes one of our big carbon sinks. So one thing is being able to pull apart the natural versus human mechanisms so we can see the role that humans play in heating our environment. And the other thing is that to produce those projections into the future, we need to be able to have some really sophisticated models. And it's really great for the modelers to be able to have some data to test their models on. So before they forecast, before they look into the future, they can use those models to kind of do a hindcast, to use their models to predict what happened in the past and compare that against our proxy reconstructions. So if there's a good fit between the proxy reconstruction and their model, then they can be more confident in projecting that into the future. So it also provides this really valuable testing ground for the models as well.
Right.
Brilliant. I hadn't, it's interesting to think about how you need all that data from the past to be able to predict into the future. And I think it's something we probably don't consider that much is that these climate models are incredibly complex computer programs, and they need as much data as possible to make sure that the calibrations are correct.
That's right. Yeah, I mean, we mentioned the orbital forcing at the end. I mean, all the models integrate all the different forcings, as Zoe said. And one of the most basic is, because of our understanding from these long records, that those small changes in the Earth's orbit, which are completely natural, and humans can't do anything about that at all, they are an underlying forcing within all the climate models, along with things like volcanic eruptions, greenhouse gases, etc.
Brilliant. Thank you both so much. I think you seem to have answered every single question that's come through, but I'm sure the students had about this, but I'm sure more will come through. But to start off with, there's a question essentially sort of, how can we help stop climate change? And it's an interesting one based on what you've talked about. Is there's some climate change what climate change do we want to stop, and how do we do it?
Shall I take it? Yeah. I think the Earth's climate has always changed, and some of these mechanisms that change the climate are completely out with human control. And for instance, the change in the output of the sun is a really good example. Changes in the Earth's orbit is another good example. But there are others which human activity have profoundly altered. And of course, the main one is, but not the only one, but the main one are the amount of greenhouse gases in the atmosphere. Now, we've seen that greenhouse gases do vary naturally, but we've now put greenhouse gases into the atmosphere to the same level that we had the last time the Earth had the same amount of greenhouse gas in its atmosphere was an extremely warm period called the Pliocene, which was over 3 million years ago. So we're getting into uncharted territory climatically in terms of recent geological time. And so we need to try to do something about the things that we can change, but accept that the Earth's climate has and will always change.
I was going to say, just to add on that, I guess when maybe the question itself was talking as well about kind of what can we do to change climate change, in our individual actions. And this is obviously a really, hot topic at the moment. As James said, like we can't influence and we won't ever influence those kind of big orbital mechanisms, but things like releasing greenhouse gas emissions and deforestation and replanting, those are things which kind of we can do individually, and societally we can make small individual actions or societal choices to be able to reduce greenhouse gas emissions. And I'm sure lots of people are aware of kind of the small things that we can do, using our car less and making some small dietary changes, or there's people will be aware of a lot of these things. So there are individual actions that we can take.
But there are some quite exciting technological developments, which together are called geoengineering. Some of you might have heard of the Orca site in Iceland, where they're actually using geothermal energy to suck CO2 out of the atmosphere. They then bury it deep under the ground where it forms a rock. So it's buried away and it can't get back into the atmosphere. And within the University in Exeter here, we have pilot projects that are actually taking CO2 out of the ocean. And that's a very effective way, because CO2 gets into the ocean from the atmosphere. So by doing that, you're reducing the greenhouse gases in the atmosphere. So it's personal behavior, it's institutional behavior, but we need everything basically, because we're in a bit of a hot spot, to be honest.
It's amazing how the science is coming on, like with this carbon storage, it's a great time to kind of be thinking of like innovation for kind of, reversing and preventing some of the human impacts.
I mean, it's fantastic. I mean, that's questions of Royal Harbour Academy really saying, all the messaging that we get is on behavioural change, as individuals. And you're talking about some of the technology. I mean, I imagine there's a balance. We probably need to do everything, at once and faster.
We absolutely do. And just because we're beginning to develop some technologies that are doing things like sucking CO2 out of the atmosphere, that is not an excuse to say, okay, then I'll just carry on burning all my fossil fuels and living in an extravagant way in an environmental sense. Because we need both. We need the behavioral change, we need the renewables. We also need to look for these other more technological processes as well.
And just for both of you, has studying climate science changed your behavior or your attitudes to the current climate crisis?
Yeah.
I was going to say it has profoundly changed my behaviour, actually. I was on a research cruise just a few years ago, researching the impact of the loss of ice in Antarctica and its impact on sea level. I was phoning home. I was phoning my daughter, who's 20, and she said, doesn't it bring home to you the fact that we all need to do things? And she said, how do you really think you can carry on eating meat, because it consumes huge resources, huge amount of land, and it provides greenhouse gases to the atmosphere. And I stopped eating red meat at that point, actually. And the reality when you're face to face with it, as I was, is profound. And I've made all sorts of changes in my lifestyle, as a lot of our colleagues have, who are seriously worried about this.
Yeah, I would completely agree. I don't think you can be this close to the data and to researchers that are kind of in your institute that are telling you this information without it really hitting home and you really wanting to participate and make the most difference that you can. So up to your ability. Some things are kind of there are some things that can be quite difficult to change, but you can use I like to use some like Geeky Zeros, like a website that shows you like small carbon, small actions that you can do to reduce your carbon footprint, because of course we can't all do everything. So it's kind of just doing what you can with the resources that you have available.
And the way, if you're worried about it, the way to kind of offset that is to have some agency, to actually do something, to actually get involved, whether that's politically or whether it's in your changes in your lifestyle or talking to people in your friends and family. If you take some agency rather than just sit back and say, oh, there's nothing we can do, that makes the situation worse for you personally, I think. So I think having some agency, because people say to me, don't you lie awake at night worrying about this? And actually, I don't. And it's because I'm in a fortunate position where I can actually try through various means to do something about it. And I think that's the key for personal well-being in this difficult situation.
And I would completely agree. And one thing I've started doing since last year, when I found that sometimes these conversations, they do get to you and they do make you feel like it's quite sad and despairing, is to seek out positive environmental news, because there is really amazing stuff going on all over the world in terms of protecting areas of forest or areas of seagrass, that are amazing carbon storage areas, or different countries taking on different targets for their renewables. There is good stuff happening in the world. And I think seeking that out to kind of keep you going and keep you thinking like you're fighting, like, and there's, something can be achieved is really powerful as well. So staying positive in the face of this quite big, scary thing is important.
The final question, James, and so sadly we've only got time for this, is how can we help people to choose to make changes in their own lives? You're obviously very close to the issue. What one thing would you say to somebody to say, how can you share that sort of sense of urgency with other people?
It is quite difficult. I mean, I've been involved in quite a few outreach sort of projects, and there seems to be something in the human makeup that if you have two views, you have climate skeptic views or you have a strongly environmental green views, that if somebody like me goes to talk about the evidence, it seems to entrench the views. Those who are environmental become more environmental, and those who are skeptical for some reason become a bit more skeptical. And very often the psychological research demonstrates its personal impact. So if a family or a community is impacted by a flood or a climate extreme, it actually brings it home, and those are the things that change behavior. So I find that quite a difficult question to answer, because you can, if you're sometimes in these situations where you're talking about the evidence, you can polarize the debate, and it's often personal experience, as is the case with us, doing the science, that is the thing that changes your behavior.
Yeah, and thinking about kind of if you're going into a conversation with someone and you want them to maybe be more engaged with climate change, is thinking about their interest, because people connect with climate change due to different issues. It may be that they live in a coastal area and they're worried about their properties or their businesses. It may be that they really love like plants and animals and they're worried about coastal habitats or the rainforest. So I think different people you can connect to on different topics. So it's kind of also figuring out what the person, your friends, your families are interested in, and trying to personalize that conversation, and then talking about it in a way that's kind of friendly. And it's quite hard sometimes to not make these topics kind of emotional. But I think if you can keep the note positive and about like us collectively changing together, that it's not like, because it's quite easy, I think, sometimes for people to feel like quite attacked on these topics if you're not. I think that's, again, is an innate thing.
I think for me, another key thing is co-benefits. So that if you can demonstrate that you're not just doing something to help the climate situation, but you're doing something to help something else. So a classic example is cycling. Cycling, you're helping your own health, but you're also helping in terms of climate. Another one is afforestation, because you're helping to mop up carbon dioxide, but you're also fantastically helping biodiversity, and you're helping human well-being as well. So I think co-benefits are really important to consider. What are the other things that would benefit from doing a certain thing?
Thank you both so much. Very, very sadly, that's all we have time for today. It's been absolutely riveting. And I've always wondered, when we see these graphs from the past however many million years, how they're created, where they come from, and it's been fascinating to get more in-depth information on that and how we can use that to help us in the future. So thank you both so much. Thank you so much to all the classes who have been watching from around the world. Been absolutely fantastic. Hope to see you all again soon. And thank you again to Zoe and James. Thanks so much.
Bye.
Bye.